Okay, good morning, everyone. So my name is Kyle Shen. I'm a professor here in the physics department at Cornell. And so today I'll be giving a 30-minute pedagogy talk on angle resolved photoemission spectroscopy. And I know since this is a very multidisciplinary crowd where there's various people working in accelerator physics and the beam storage and things like that, I've tried to make this a very general overview so that hopefully everyone will be able to understand what I'm talking about. So generally speaking, the reason why, and one thing I also want to do is I'll just mention that there's obviously a lot of photoemission involved in the beam production aspect of the center. Most of that happens at very low photon energies. Most of the photoemission I'll be talking about, conventional angle resolved photoemission spectroscopy happens at fairly high photon energies relative to the kinds of things we'd be doing with photocathodes. Okay, so I just wanted to put that out there. The reason why people are generally interested in photoemission spectroscopy is that it's a very direct probe of electronic structure, and it's what we call a photon in, electron out technique. So basic idea of how it works is a photon comes in, if it's energetic enough, it can eject an electron off the surface of whatever material you want to study, and then it'll come out with some energy and momentum. And the basic principle is, using conservation laws, you use the information about the energy and momentum of the photoelectron coming out to back out some information about the electronic structure inside the solid. Okay? And when I say spectroscopy, what that really means is simply that it's an energy resolving technique. So what we're doing is we're measuring, in this case, we're measuring the kinetic energy of the electron, and that gives us the sort of energy resolved information. So when you see spectroscopy, it just means energy resolved. Okay? And so I'll just contrast that. So many of you are familiar with things like Raman spectroscopy or optical, spectroscopy, ellipsometry, X-ray diffraction. Those are photon in, photon out. Electron in, electron out are things like electron microscopy and things like that. Okay. So there's some, particular advantages for using photoemission spectroscopy for certain things. So it's highly surface sensitive. So typically you have sensitivity on the order of a 1 to few nanometers. So that can be a pro or a con, depending on what you're after. One of the nice aspects of it is it gives you elemental information. All right, so if you look deeper into the electronic structure, you can see core levels that correspond to, let's say if you want to know what oxidation state your copper is in, photoemission spectroscopy can tell you that. Chemical information, as I just mentioned. So if you measure sort of close to the Fermi energy, so the highest occupied states in your crystal, you can get information about the electronic structure. So the Fermi surface, the band structure. So things that if you've taken a solid state physics class in Cattell or Ashcroft and Mermin, the kinds of things that you would calculate, you can measure directly. Okay, and so in many materials, it turns out that the simple calculations that one does is maybe not very accurate. And so it's very useful to have sort of a direct probe of that electronic structure. And then it's fairly efficient, so it's fairly large cross sections. All right, and so just a very brief rundown of the history. So it was discovered, so a lot of people associate photoemission with Einstein, of course. This is actually what he won his Nobel Prize for I forget when. So 1905, of course, was that famous paper. Discovered sort of in the late 1800s by Hertz and others. And then it wasn't actually until the sort of 50s, 60s, people actually started to use it for things, okay? And it really wasn't until about 30 to 40 years ago that people started to actually use this as a tool for trying to understand materials, for actually measuring the electronic structure of materials. So it's I would say, it's, to this point, I would say mature, but, it's not as old a technique as, let's say, X-ray diffraction or something like that. And so, very simple picture of how this works. If we just start with just an atom in free space, right, is you just have core levels, 1s, 2s, And so as if you come in with sufficiently high energy photons, let's say X-rays, just energy conservation will just, eject them to some free electron state. So let's imagine you had a little detector, right, and you would be measuring the kinetic energy. You would just basically measure these core levels that would correspond to the energy levels of the, of the electrons when they're inside the ion. One of the nice aspects is that you don't have to be on any kind of particular resonance, right? So there's a lot of things where you know, like NMR and things like that, where you have to be exactly at the right frequency to induce some kind of transition. Here you're transitioning to some just free electron state that's outside the crystal, that's just propagating in free space. And so you don't really need to worry about being on any kind of resonance. Now, I'll be talking about, so in that case, this is from an atom. I'll be talking about angular resolve photoemission spectroscopy, which is has its greatest utility for things like, you know, for crystalline solids. And so if you think of a crystalline solid, so we now take that, you know, sodium ion or atom, and we now put it in a lattice. Of course, what happens is that the states, the highest energy states will hybridize, right, and form bands. And so that's these, you know, the states at very high binding energy won't do very much, right? So these are very high energies, but the highest occupied states here will start to hybridize and form these electronic bands. And that's this green, you know, so now it'll form this kind of green stuff here. And so, you know, you'll basically be able to probe this, right? This is in a very simple cartoon picture that neglects momentum. And so, okay, so actually I'll skip this one. So the very simple, just sort of nuts and bolts of how the experiment works is, so you have a photon beam. Typically, it's in the ultraviolet. And I have another slide on this in a second, but sort of in the tens to hundreds of electron volts energy range. You'll have a sample that's actually not floating. It's connected to the ground of the chamber, okay? So for a lot of the experiments we do, it's at low temperature, so there's some kind of ultra-high vacuum cryostat. And then, you know, photoelectrons are just emitted in all directions. And then you have some spectrometer, and basically it's just collecting electrons. And so what you have is you have a pair of hemispherical detectors, which I think is on my next slide that I'll show. And it's basically just an electrostatic lens that allows you to measure the energy and momentum of the electrons, and also, so actually, if you think of the simplest way this works, right, you could just imagine a pinhole. And so the orientation of your sample relative to the direction the pinhole is facing determines the momentum of the electrons coming out, or at least the direction, the angle. And then if you measure the speed with which the electrons are coming out, just using some simple electrostatic plates, then you get the energy, right? So now you have the energy and the directions, so you can back out the momentum of the electron relative to that of the sample. If the sample is crystalline, then you orient that relative to the crystallographic axes, right? Your reciprocal lattice vectors. So that gives you that basically allows you to take this object and map it back into K and energy inside the solid. So one catch is that this all has to happen in very high vacuum. So this is all sort of typically 10 to the minus 10 or 10 to the minus 11 torr. Photoemission is a very surface sensitive technique. And so what happens is that, you know, in this room, we'll have lots of molecules adsorbed onto surfaces. If you had that actually happening here, then the photoelectrons, as they come out, will get scattered, okay? And so you'll lose that energy and momentum information. So what you want to have is an atomically clean surface. And to have an atomically clean surface over the course of, you know, many hours or a day to do your measurement, you need this kind of vacuum, okay? The ballistic mean free path of an electron here is also, you know, going to be, you also don't want to be in air, but it's actually much larger than it needs to be for this pressure. So typically speaking, the energy resolution, let's say, of a typical electron analyzer, so if you're doing like X-ray photoelectron spectroscopy, which I think a lot of you have done, like XPS to characterize, you know, chemical information, the energy resolution of your detector might be sort of tens of millielectron volts. The best systems, the best electron hemispherical detectors we have to date kind of give you about a 1 millielectron volt energy resolution, which is quite good. So, you know, so this is sort of energy scales on the order of, you know, few Kelvin, okay? So it's quite low, you know, sort of high energy resolution. And so effectively what you're doing is just placing a voltage potential between these plates. You have an electron coming through, and so obviously only electrons with the correct energy will make it all the way around, right? If they're too fast, for instance, they may slam into this outer plate. If they're too slow, they'll get sucked into the inner plate, right? And so there's something called the pass energy, which is the energy that this thing needs to have to make it all the way around. There's a detector here, okay? And so, you know, the fact that we don't have magnetic monopoles in free space makes magnetic lensing quite difficult. So generally people stay away from magnetic lensing. Electrostatics is much easier to control. And this thing is usually just some kind of channel plate, you know, channeltron, or in our case, you know, we use some kind of multi-channel plate. And the thing is, measuring electrons is pretty easy, right? So this is not, we don't have to use any kind of exotic tools here. So this is sort of close to the state of the art in terms of what people have to date with electron analyzers. So again, it'd be these hemispheres that I showed in this previous slide here are basically inside the back of the stainless steel dome. So the technology behind these spectrometers has increased quite a bit over the last, let's say 3 decades. So here is a measurement of the same surface state, the same sample. It's a surface state of silver, if you will. And so you can see that it's getting sharper and sharper and sharper. And so at this point here, what I'll say to date is that with today's generation of analyzers, we're really measuring, in most cases, the intrinsic lifetime of the excitations that we're generating, okay? So here, we're just measuring the instrumental resolution, which is not very interesting, right? And so, like I said, because you can get down to very high energy resolution, so this is less than 1 millielectron volt. With a cryostat, we can get down to temperature sort of, the best people have done is sort of down to a couple Kelvin. So you can measure now, for instance, the superconducting gap in some low temperature superconductor where you can see that, there's some shift away from the Fermi level. This is in millielectron volts by, let's say, half a millielectron volt. This is a very challenging measurement, but it's sort of, an example of what can be done with this technique if you're interested in these kinds of problems. So it turns out that you can use a lot of different photon sources to do photoemission spectroscopy. So for those of you, like I said, that have done things like X-ray photoelectron spectroscopy or XPS, it's usually just an X-ray anode that's, again, in your ultra-high vacuum manifold. In our lab, we use a series of, we use a plasma discharge lamp. So what you do is you drive some, in this case, it's some inert gas. We're using helium. We drive helium with some microwaves, and it has various resonances, and so they'll emit in sort of the tens of electron volt energy range. Okay, probably the place of choice to really do these photoemission measurements is really at synchrotrons, and so particularly the Advanced Light Source at Lawrence Berkeley Lab, the Stanford Synchrotron Radiation Lab at SLAC. Those have a bunch of beamlines that are optimized for doing photoemission spectroscopy. One thing I'll mention is that, so for instance, you might ask, well, why don't people do photoemission here at Chess, right? We have a synchrotron here. And the reason is that we want relatively low energy photons, so something on the order of, tens to 100 electron volts of photon energy. So Chess is optimized for kiloelectron volts. And so, what's wrong with kiloelectron volts? So in principle, you can do photoemission with kiloelectron volt photons. The problem is that the photoemission cross-section drops very precipitously once you get up to those energies. So you're operating at something that might be 2 or 3 orders of magnitude less intensity of your signal than if you were operating at like 10 electron volts or 100 electron volts. So there's a few synchrotrons out there in the country where they're sort of optimized for doing these kinds of experiments. And then for instance, the stuff that's being done here at CBB is really using lasers, and there's other people that use lasers as well. So the advantages of using a laser is that you can generate very, very high intensity pulses, which is, for instance, why people use it here for photocathode research. One problem with lasers is that it's very hard to get lasers to have sufficient energy lasers at sort of in the energy range where we want to do these experiments. So if you think of your typical laser pointer like here, right, this is sort of an electron volt energy. And it's very challenging to get up to even 6 or 7 electron volts. You have to use various kinds of stages of higher harmonic generation. To do that, every time you do that, you're tossing out photons. So typically getting up to 6 or 7 eV is sort of what most people can do to date. There's a couple sources where you can get up to about 10 electron volts, but you're really pushing it. So they're just much less common in general. Getting to 6 eV is relatively straightforward. And of course, in order to do these experiments, you want a monochromatic photon source. You want it to be fairly high intensity, so something on the order of 10 to the 9 or 10 to the 10 photons per second that you're illuminating your sample with. And they, again, have to be energetic such that you can pull the electron out of the crystal. And so a typical work function for a normal material, so not, let's say, a photocathode where they have let's say a negative electron affinity, but let's say an ordinary material like, a piece of aluminum would have a work function on the order of, let's say, 4 to 5 electron volts. You need photons above this energy. And so this is sort of a schematic of how these experiments work at a synchrotron. So you have your synchrotron here. They pass through these what are called insertion devices. Here's an undulator. So this basically squeezes all the power into a fairly narrow spectral range by wiggling the electrons back and forth. There's a bunch of beamline optics, so various kinds of gratings to give you much better energy resolution. You have these little exit and entrance slits that you can use to control the photon energy and the resolution. And then here, and one challenge is that is because sort of in this 10 to 100 electron volt range, there's not any good windows. So everything has to be tied to, everything is actually connected in vacuum. And so there have been instances that, at least fortunately that I personally have not been involved in, where an accident on this, on the chamber here caused the entire synchrotron to get exposed to atmosphere, and then you have a lot of unhappy customers, and then people, with pitchforks and torches trying to find who did that. So, so that's one of the challenges of working these energy ranges. There's really no efficient windows. And so again, this is all sort of in 10 to the minus 10 or 10 to the minus 11 torr, and then you focus your photons down to the sample. Again, another challenge in this energy range is there's no good lenses, so you have to use basically some kind of reflective optics. And then, but you sort of get a photon beam typically down here with energy spread on the order of a few millielectron volts, and then the electrons fly out all over the place in the chamber, and you have this detector that's collecting them, okay, and measuring their energy and momentum. So again, as I mentioned at the very beginning, one of the challenges of doing photoemission is that the mean free path of a photoelectron inside a crystal is about 1 nanometer, okay? And it's not so difficult to understand why. Electrons are all charged. They interact very strongly with one another. So the likelihood an electron will propagate very, very far inside a solid without scattering off another electron is very low, right? So that mean free path is typically on the order of a nanometer. It depends on the plasma frequency and things like that, but that's just sort of a rule of thumb. Again, as I mentioned earlier, we also need to make sure that the surfaces are pristine, so we don't have kind of hydrocarbons or water or really anything adsorbed to the sample surface, because that will scatter the electrons as they come out, and then we'll lose the energy and momentum information that we actually care about. Again, because they're charged particles moving in free space, when they move to our detector, we have to make sure that area is entirely free of any kind of electromagnetic fields. So electric fields is easy, so the entire chamber is at ground. But magnetic fields are relatively difficult, so usually these chambers have various levels of what are called mu metal shielding. It's just some very soft magnetic material that steers the Earth's field away from the chamber, okay? And so typically to do the kinds of experiments we like, we want, so the Earth's field is roughly half a Gauss, or 500 milligauss. We want to get the residual field in the chamber down by a factor of about 1,000, so sort of below 1 milligauss. So there's a lot of engineering that goes into that. And again, because you're doing all this thing in vacuum, you have various limitations on the kinds of materials you can look at, right? So looking at, I don't know, blood cells or something is probably not very feasible. First of all, the outgas. Second of all, the radiation will crack and damage it. So this has never been very useful for biological samples. Let's see here. So I think I covered a lot of this already. So again, we're doing most of these experiments at 10 to hundreds of electron volts, which means the main sources are synchrotrons, some lasers, and plasma discharge lamps. This kind of stuff is found mostly at synchrotrons, also some, just laboratory sources like we have in our laboratory. These days people use them to study all kinds of different materials. So, quantum materials are things like superconductors, topological materials. There's a whole class of research basically interested on surface physics. So, so that's sort of what this is conventionally used for. Okay, so here's a little bit about the kinematics of how this works. So again, you have this beam of photons that's coming in. As I mentioned, because we're typically not using X-rays to do angular resolve photoemission, the momentum that the photon carries is effectively negligible. Okay, so obviously in X-ray diffraction experiments, all the momentum is carried by the photon, and so here you can think of this as some kind of direct transition. Okay, so what happens is the photons come in with some energy. An electron absorbs the energy and is emitted. And so, we just use simple conservation relations. So if we know what the photon energy is of our material, and we can measure the kinetic energy, and the work function is known, then basically we know automatically what the binding energy of the electrons is in the solid. Most of the time in an experiment, we don't really pay attention to this work function. It turns out that this is usually the work function of the actual detector itself. That's not physically so interesting for our experiment. The other thing is that if we're measuring a metal, there's a well-defined cutoff, which is the Fermi energy, so we can use that to self-reference what energy we're studying. Okay, so we know the kinetic energy of the electron coming off, and because we know, the angles which it's coming off the solid, we can project that speed into various momentum components, right? This is basically, first semester freshman physics. So we basically just use these measured quantities that we measure in an experiment, and we can just back out the binding energy and the parallel momentum. So a key aspect here is that if we're working with a crystalline solid, then there's translational symmetry in this direction, right? It's a regular lattice laterally, and free space is obviously translation invariant. So we use that translational invariance to basically say, okay, the parallel component of the momentum is conserved. So if we measure the parallel component of the momentum with our detector, we can just say that's the parallel momentum of the component of the electron when it was in the solid, modulo some lattice translation vector, right? That's not the case in the vertical direction, because obviously we've truncated the solid, right? There's a surface. So the electron will lose some momentum as it comes out. So you could think of it basically as just a one-dimensional scattering problem where an electron is propagating, right? There's a potential step. The electron is coming across the step. There's some probability to reflect back, some probability to come out. Okay, so you can't think of momentum a translational invariance in this direction. If you didn't have if you didn't break translational invariance, you wouldn't be able to take anything out. So, all right. Let's see here. So I think I covered that in the last slide, so I'll skip this one. So I'll just show now a couple very simple examples of photoemission, some example systems. So let's imagine we had a system where we had the electrons were just trapped on the surface. So we just had a two-dimensional electron gas, or electrons were just free to move in the x and y plane on the surface of the material, and let's say they weren't going down to the bulk, right? And so in a lot of materials, like noble metals or topological insulators, you have electrons that are basically just propagating freely on the surface, like a 2D electron gas, right? So if you're going to plot the energy momentum relationship of such objects, right? So we're only going to be plotting them in moment kx and ky. Like I said, kz is not a good quantum number because they're trapped, they're just living on the surface. And this is the energy here. Then you'd expect some kind of paraboloid, right? If it's just a free electron gas, just no, we're not going to worry about any interactions with the lattice. And then, you would fill up this free electron gas with some energy to the highest occupied states, and that's the Fermi energy here, right? So your energy momentum dispersion would be some kind of two-dimensional paraboloid that's filled up to some highest occupied state here. And so, when we're doing our measurements, we typically measure energy as a function of momentum, so we should measure these parabolic dispersions. And if we measured the contour of highest occupied states, we should get a ring, right? That's our Fermi surface. And so, like I said, there's many examples of real systems where you actually see this. So this is a surface state of copper 111. It turns out if you just take a piece of copper and put it in your chamber, it won't work. So you have to take a nice crystal that is oriented in the right direction. You have to anneal and sputter it to get the surface nice and clean. But once you do that, you can basically measure things that look exactly like a free electron gas. Okay, so it works more or less as advertised. And then there are more complicated versions of this. This is something that I did way back when on some kind of quantum material where, again, it's not a two-dimensional free electron gas, but what we're doing here is I'm showing the data that we take as it's a quasi-two-dimensional material, so I'm not going to plot kz. We're measuring it as a function of two in-plane momentum and the energy. And you take this basically three-dimensional wedge of data, okay? And so each one of these kind of voxels, if you will, is at one energy, momentum, kx, ky, and energy. And then the false color tells you basically how many electrons you're measuring at that one point in this three-dimensional space, right? And so if I look at this false color plot, if I look at this top surface here, this is the intensity at one energy, which is the Fermi energy, as a function of kx and ky. So you can see the Fermi surface is made of these sort of intersecting circles, right? And then the, if I look at this, let's say these vertical surfaces of the wedge, that's energy versus momentum, that's the band dispersion, right? And so one thing you can do is, so I'll do here, let's see if this works. So if I sweep through from the bottom of the wedge all the way to the top, you can see that these fuzzy features down here get very sharp and well-defined. And that's telling you about how the, what the lifetime of the excitations that you're making are, okay? So it's basically, for those of you that have ever heard of Fermi liquid theory, that's basically an illustration of Fermi liquid theory, that you only have these well-defined excitations very close to the Fermi level. So I think I have, what, a couple minutes left? Yeah. All right, so I'm gonna, let's see, how many more? I have a couple more slides. And I should probably leave a couple minutes for questions too, right? So, all right, so let me just, so let me see, I'll do two more slides. And so that movie I played, right, where you had this kind of fuzzy stuff and it got really sharp, it can actually be more formally, there's actually some formal mathematical foundations behind understanding that. And so if you assume something called the sudden approximation, which it turns out for photocathodes is a very bad assumption because you're pulling electrons out very slowly. The sudden approximation assumes you're pulling the electron out really fast, okay? So we're coming in with, let's say, a 100 electron volt photon, and the electrons are coming out with roughly 100 electron volts. That's relatively fast. If they're dribbling out, let's say, in a photocathode, that's actually not a good assumption. But conventionally, we try to work in the regime where the sudden approximation is valid. Then you can decompose the photoemission intensity into a bunch of things like a matrix element, the Fermi-Dirac function, and this AK of omega. And this AK of omega is what's called the single particle spectral function, okay? And it's something, and there are these, it's made up of these what are called self-energy terms, the imaginary and real parts. And these things encode the interactions, okay? And so for those of you that have ever studied, I don't know, some kind of field theory, like quantum field theory, you know that you learn how to sum different kinds of Feynman diagrams up. And so what you can do is you can write down different kinds of interactions and sum them up and then generate these things theoretically, and then you can compare them to experiments. So for instance, if you're interested in like, it is what I see in my photoemission experiment due to an electron-phonon interaction or an electron-electron interaction, you can actually be able to quantitatively compare those things by analyzing the data in various ways. So I guess I'll end with this one so I can take, I don't know, I have 1 minute for questions. So here's an example of some work we did a while back, and this is in a material called strontium ruthenium-03. It doesn't really matter what it is. So the main thing is that if we measure the band dispersion, what we see, it's maybe not coming out so great here, but hopefully what you can see here is that right around where my laser pointer is, this kind of this feature here starts to kind of kink over. It looks like a little, hopefully you can see it looks a little bit like this. If I extract the energy momentum dispersion, you can see there's a wiggle here, okay? And so that's a very characteristic signature of electrons interacting with some collective mode. So in this case, it turns out this is some kind of phonon. And so if you look at page 521 of Ashcroft and Mermin, which, we're at Cornell, everyone needs to memorize Ashcroft and Mermin, then, you see something very similar here, right? So they're saying, okay, if I have an electron interacting with some phonons, I should see some kind of wiggle, characteristic wiggle, away from the free electron dispersion, which is what this blue line is, okay? And this is sort of a nice way of looking at the, of being able to extract different kinds of interactions in the solid that, are very difficult to extract using other kinds of techniques, okay? So I think my time is up, or almost up. So I have time to maybe take a couple questions if there are any. Yeah.
So you said the resolution at the moment is just a little bit less than 1 millielectron volt.
Yeah, I mean, that sort of depends from system to system, but sort of the state of the art is sort of, yeah, that's right.
But the feature you're pointing at here is at the like 100 millielectron volt
Yeah.
level. So does that mean that 1 millielectron volt is as good as you need to do, or would you start seeing things?
Yeah, so for this particular, experiment, this measurement was probably done with about 5 or 10 probably closer to 10 millivolt resolution. And so if you're interested in this, that's really all you need to do, right? If you're interested in some very subtle feature that's maybe living right there, you would want to do better than that, right? So
What might that be? What might that feature be?
So I'll give you one example. So one material that we're interested in our research group is a material called strontium-2 ruthenium-04. It's purported to be a topological superconductor, and people are interested for quantum computing, possible quantum computing applications. The problem is that superconductor is only 1.5 Kelvin, and the energy gap is very tiny. It's like micro electron volts. So if you wanted to know more about it, you'd have to have that kind of resolution. So it's kind of depending on what problem you're interested in, you may or may not need that better resolution. All right. No other. Yeah.
Can you see hydrogen with any kind of photoemission spectroscopy?
Can I see what?
Hydrogen.
Oh yeah. So I mean, so there's also a class of experiments that people do on like gaseous photoemission, and so people have done there's been very famous experiments where people measure the photoemission spectrum of like diatomic, of molecular hydrogen. That's probably what you're like just a hydrogen molecule? Is that what you're asking?
Just the usual XPS don't see that for some reason.
Oh, so in XPS, I mean, it's just the core levels are very shallow, right? Because you only have the 13.6 EV. But yeah, no, I mean, people have done a lot of experiments measuring the Frank-Condon factors, molecular hydrogen. Usually they do that at like, not with X-rays, so they'll do that with maybe, 50 electron volt or 100 electron volt photons. But yeah, there's been a lot of work done in that avenue. So, okay. So I think, I guess our next speaker is Matthias. So I think I will.